27th lecture in the lecture series on nonlinear dynamics being conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. Now it's my great pleasure to introduce you today's speaker, Professor Malay Banerjee from the Department of Mathematics and Statistics, IIT Kanpur. Though I have not met Professor Banerjee in recent times, and I missed his conference at IIT Kanpur, NCNST, which he organized 5 years ago. I think Professor Sendilwalan had attended the meeting and he had interacted with him. And he also, Sendilwalan had also attended another meeting at University of Kalyani later on. And there he had invited Professor Banerjee to visit our center, our department. And he had also kindly agreed, but that was before the pandemic started. So unfortunately, due to this pandemic, he could not come. And we do expect him to visit us sometime in the near future. Now, Professor Malay Banerjee had his academic career in Kolkata, and now he's a full professor in the Department of Mathematics at IIT Kanpur. Professor Banerjee is an expert in mathematical modeling. He's also one of the few scientists working in the area of mathematical biology from the nonlinear dynamics point of view, from the nonlinear perspective. In particular, he works on the topics like mathematical ecology, pattern formation, and spatiotemporal chaos. He had published lots of papers, I think more than 170 papers, etc., on mathematical biology, and his works are well known. And he has also trained a large number of people in mathematical biology. He's also serving in the editorial board as a board member in some of the popular journals in nonlinear dynamics. This short introduction, now I welcome Professor Banerjee. Low fast scale on spatiotemporal pattern formation. So Professor Banerjee, please take over.
Thank you. Thank you very much for your kind introduction, and let me share my screen. Can you see my screen?
Yes, sir. Your screen is visible.
Okay.
Is it visible? I don't see that.
The screen is visible now, sir. Sir, your voice is breaking, sir. We cannot hear you.
This is for me.
Yes.
Okay. Okay, so thank you very much for your kind introduction and kind invitation. And it is unfortunate that I missed the opportunity to visit your campus. And actually, that was my last visit for some offline talk before the pandemic. And after that, that was in Kolkata University. And after that, we are keep on continuing on online mode. So today I'm going to talk about the effect of slow fast time scale on spatiotemporal pattern formation. So in this talk, first I will provide some brief introduction about the preliminary ideas which are involved with the spatiotemporal pattern formation. And then I'll come to the discussion about model with slow fast time scale. And then I'll come to the spatiotemporal pattern formation, and then I'll introduce another new idea, that is model with non-local interaction. So let us start with some example. So this is a nice example of spatiotemporal pattern formation, but in the context of animal skin pattern. And this is the pattern seen on the juvenile empire angelfish. If we look at the adult emperor angelfish, so pattern gets changed, and this kind of patterns was initially studied in the context of morphogenesis, chemical morphogenesis, and a varieties of this skin pattern is well studied, and a gallery of such kind of pattern can be seen from here. So J.D. Murray and his group, they developed a very nice theory such that depending upon the growth from embryo, these patterns can be traced out, and they have obtained different and proposed different mathematical models such that these kind of patterns can be captured. But in my talk, I'm not going to talk about this kind of pattern formation. Rather, I'm going to talk about pattern formation in the context of interacting population. So this is an example of a that is labyrinthine pattern produced by ribbon forest. And in this figure, you can see the way these trees are distributed. So if we consider the large or that is the long trees as a collection of the focus biomass, then we can see their distribution somehow looks like labyrinthine. And this enlarged picture clearly shows that human intervention is somehow responsible for generation of this pattern, but there are some other chemical and that means nutrients available in the soil and water current during the rainy season. These are also responsible for generation of this kind of pattern. But this is an example where we can see labyrinthine pattern in nature. Now, if we look at this kind of wetland vegetation, so this also shows two different kind of patterns. If we consider pattern at this on the left panel, then over the water bed, the vegetation actually creates a pattern at different positions, and here the spots which are generated, that is due to the presence of the vegetation. On the other hand, if we look at the pattern on the right hand side, so then we can see the spots are generated due to the absence of the vegetation. And based upon this idea, two different stationary patterns are studied in the context of mathematical modeling. Those are called hot spot pattern and cold spot pattern. So pattern on the left, you can see that is hot spot pattern because spots are due to high concentration of the focal species under consideration. On the right hand, this is called cold spot pattern because spots are generated due to low concentration or due to the absence of the vegetation here. Again, if we look at this kind of dynamic pattern, although it is a snapshot, but each and everyone can understand that this picture will not remain same for all time points, rather it keep on changing. And in this case, again, you can try to think about some kind of spots we can see at different location, partly here, partly at this position, partly at this position. And you can see that these spots are due to the presence of the predator, where it is a yellow shark, and they are surrounded by their target prey, that is bluefin tuna. So bluefin tuna, they also produce spot pattern, but that is cold spot with respect to bluefin tuna because spots are visible due to absence of that particular individuals in this particular location. And again, in the context of predator, what we can see, the spot pattern, and this is hot spot pattern because spots are somehow generated due to their presence at some disjoint location. And the fundamental difference between the patterns that I have shown in the last slide and this slide is that Earlier one is a stationary pattern, but this one is a dynamic pattern. So mathematical modeling of previous pattern is quite easy compared to this one, because in this case we need to incorporate the concept of game theory into the picture. That is how they are approaching towards the fish school and trying to catch the individuals, and then they disappear once they are able to have some successful catch. But the idea is that these kind of patterns can be categorized into three different format. One is called random distribution, like you can see some flowers at different location. This is a clumped pattern, so a group of animals, they can move from one location to other location. And this is a uniform pattern where they stand at more or less equidistant way, and this is called a uniform pattern formation. So the point is that again, these two patterns are instantaneous, rather in terms of mathematics what we say, these are dynamic in nature, so they keep on changing. They can rest at this particular position for certain time period, but not for a longer time period. But here you can see once the flower appears, they might last for a couple of days, or for some other species maybe a couple of weeks, but slowly the flowers blooms at other location, and then it is a random distribution with respect to slowly varying time period. But these are some examples that mathematical model can generate these different kind of patterns. So left panel you can see the mathematically reproduced cold spot pattern. In the middle panel you can see the labyrinthine pattern, and on the right you can see hot spot pattern. Again, just for cross verification, you can see the spots are blue in color, and that is due to the low concentration of this component. And on the right hand side you can see spots are red in color, which are generated due to high concentration of the component. And there are some other kind of patterns also. This is the phytoplankton bloom in the coastal area of California, and the picture was taken by NASA, and further details you can find from this particular link. And this kind of pattern is also captured by some mathematical model, and then numerical simulation reveals that we can have, or we can capture this kind of pattern, and that looks like this one. Of course, in earlier case the domain was not squared, but this is an approximation of such kind of pattern over a squared domain. Now the question is that which kind of model, or what kind of mathematical model is required to capture this kind of pattern formation? Answer is that whatever pattern I have shown you, that is through numerical simulation, those are all generated through this type of two coupled nonlinear parabolic PDE. Here F1 and F2, they describe the reaction kinetics between two species, and these are the diffusion coefficients. And this term on the left, it describes the growth of the two component of two species with respect to time. And D is a dimensionless quantity, which is the ratio of diffusivity of P over the diffusivity of N. And for simplicity, we can consider squared domain subjected to positive initial condition, and also we are assuming without any loss of generality no flux boundary condition. That means there is no influx or outflux through the boundary. So this is the simplest format through which we can capture the spatiotemporal pattern, and the pattern can be categorized into different types based upon the reaction kinetics and other stability analysis. So mostly we find stationary patterns through Turing instability, but there is variety of dynamic patterns. Those includes traveling wave, periodic traveling wave, modulated traveling wave, pulse, spitting pulse, moving pulse, as well as spatiotemporal chaos. Within this talk, it is difficult for me to go through all of them individually, but some of them I'll cover in the coming slides. So this is a practical example of mathematical modeling and validation with the realistic scenario. If anybody interested, they can see this particular paper. They have explained that these three different types of pattern can be captured through a single partial differential equation, and in order to capture the irregularity in the size of the spots, they have introduced some sort of noise terms. So these equations is little bit complicated because these are not only reaction diffusion equation, rather reaction diffusion equations are influenced by some environmental perturbation just to take care of environmental perturbation which is responsible to generate this kind of irregular patterns. But this is a nice example through which you can see that three different types of vegetation pattern that can be produced through numerical simulation of particular one model due to choice of different parameter values. So in this talk, what we are going to talk about, that is mainly interaction between population, and we are familiar with this kind of food webs, and these food webs or food chains, those are quite complex in nature because it actually consists with several network structure. But in order to simplify our mathematical modeling approach, what we can do, we can just consider different trophic level. These are the examples of two different trophic levels. Left one can be considered as an aquatic trophic level, and the right one can be considered as a forest trophic level. And when we are talking about prey predator or resource consumer kind of interaction model, those are actually consist with interaction between two trophic levels. That might be between basic trophic level or primary producer and primary consumer, or it may be interaction between primary consumer and secondary consumer, or it might be interaction between secondary consumer and tertiary consumer. Of course, we can have some sort of longer food chain, but these are some representative simple examples of food chain which consist with 3, 4, or 5 trophic levels. So when we consider the resource consumer kind of model or prey predator kind of model, those are actually building blocks of different food chains. Now, this is a just simple representation. If anybody interested, they can have a look at this particular data. It actually explains the non-uniform growth of different species over a time period, and the next slide also shows some sort of growth rate and their body size in case of wildlife ecosystem, where we can see that prey and predator, they are not growing over the same time scale. Rather, if we measure the growth of the two species with respect to a particular time scale, then we can find one species is going comparatively fast and another species they are growing over a slower time scale. So these are some sort of ecological data which supports the formation of a mathematical model with so fast time scale. But before going to talk about slow fast time scale, let us consider a very simple and standard ordinary differential equation model for prey predator type interaction, where the prey grows in the absence of predator following the logistic growth law. Of course, this model is written in terms of dimensionless parameters. That means this model is rescaled such that u, v, time, these are all dimensionless variables, and alpha, beta, delta, these are dimensionless parameters. So the idea is that here we assume that in the absence of predator, the growth of prey follows the logistic growth law. So if we rewrite this equation as u into 1 minus u, so then we can understand that this growth rate is positive whenever u less than 1, and it is negative whenever u greater than 1. And once the predator consumes prey, then the interaction is modeled by this particular term, and this functional response, that is alpha u by delta plus u plus v, which describes the per capita consumption of the prey by the predator and also known as functional response, that follows the Beddington-de-Angelis formulation. And it is assumed that predator is specialist in nature because you can easily verify that if u is absent, so that means if you substitute u equal to 0 here, so then predator goes to extinction exponentially, because delta is a positive parameter which measures the intrinsic death rate of that particular species in the absence of available food source. And as the predator goes to extinction in the absence of prey, so that's why it is called a specialist predator. So now what we can do here, we can introduce a slow first time scale with the assumption that predator grows over a slower time scale compared to prey. And that's why we are introducing a time scale parameter epsilon here, where epsilon satisfies the condition that it lies between 0 and 1. So therefore, we can have this system where epsilon is a time scale parameter lying between 0 and 1. And of course, we can write the equation in terms of slower time scale. So here T is known as faster time scale. And if we rescale the model by replacing epsilon T equal to tau, then we can describe the model in terms of slower time scale. So in order to understand the dynamics of the system, mostly we consider two different subsystems. So first of all, we can consider the fast subsystem by assuming epsilon is equal to 0. Of course, this is a singular limit. You cannot have the dynamics of this system as a limit of the previous system. So that's why it is called a singular limit. But as we are considering epsilon equal to 0 and the model is written in terms of the time t, which is known as the fast time scale, so therefore it is called the fast subsystem. And if you solve the second equation dv dt equal to 0, then you can find that v equal to v0, that is the initial value of v what we have assumed. And then if we substitute this v0 in this equation, then it becomes a single variable equation in terms of u. And you can easily analyze the dynamics of this system by finding its equilibrium point and also checking the linear stability of various equilibrium points of this system. But keep in mind that equilibrium points of this particular system is solely depends upon the choice of V0. So that means V0 plays a crucial role in order to ensure the existence as well as feasibility of the equilibrium point. But what we can understand that once we choose a particular point V equal to V0 and V remains V0 for all time, so it means that fast subsystem produces a motion which moves or which is described only along the horizontal line, because most of the time we consider u in the horizontal axis and v on the vertical axis. So therefore v equal to 0 and u is changing with respect to time, that gives us a motion on a horizontal axis. Now if we consider the slow subsystem, that means transferring epsilon into the first equation by rewriting the equation in terms of the slow time scale, that is tau. So and then finally substituting epsilon equal to 0, you have a slow subsystem. And the slow subsystem is actually an algebraic differential equation. There is some particular theory that how this can be studied, but I am not going into the details at that particular stuff. But the idea is that if you start from a point, it is better to consider a point on this particular curve in 2 dimension, and then you solve this equation in order to find out the next position of v, and then again you go back to this equation in order to determine u, come back to this equation, and in this way you can find out its solution. But what you can understand that its solution consists with 2 different curves. One is given by u equal to 0, that means either this equation will give you a straight line u equal to 0 or a curve that is given by 1 minus u minus alpha v by delta plus u plus v. And depending upon the position of u and v, we can find whether v is increasing or decreasing, and accordingly you can find the motion of the solution along the curve either u equal to 0 or 1 minus u minus alpha v by delta plus u plus v equal to 0. Now I will show you the dynamics of these 2 systems separately. So first let us try to understand the dynamics of the first subsystem. So this is the dynamics of the first subsystem, and in this case what you can see that if your choice of v0 above this particular threshold, of course for a certain choice of the parameter values of alpha, beta and delta, there is no equilibrium point. But if V0 is less than this threshold, then you can find 2 equilibrium points up to this level. But if it is below this, then you will find only 1 equilibrium point. And these green dots represents they are stable, and red dots represents they are unstable. And as a result, you can see at this position, if you choose some initial condition, solution will move towards this stable component. Whereas if you choose some point here, then it will move away from this equilibrium because this is unstable. And if you choose some point here, then looking at the equation and also the derivative, that means sign of the derivative, that is du dt, you can find u is always negative. So therefore solution trajectory moves in this particular way. So this is a representation of the fast subsystem. And slow subsystem, that is confined within these two curves. This is the line u equal to 0, and this is the line 1 minus u minus alpha v by delta plus u plus v. This is actually a fault point. This is a transcritical point. So the actual solution of the complete system is just combination of these two systems. Of course, these are the limiting system. Now I will show you that how the dynamics of the system changes if we change the parameter value epsilon from its standard value 1, where we assume there is no difference in the time scale. But I will show you that how the dynamics changes with the assumption that prey and predator, or resource and consumer, they grow over 2 different time scale. So this is the position of the limit cycle. So that means you have one null line given by this red dashed line. This is the predator null line, that is the black dashed line, and their point of intersection is the coexistence equilibrium point for this choice of parameter values, which is unstable, and that is surrounded by a stable limit cycle. This is the value for epsilon equal to 1. Okay. So now if we change the value of epsilon from epsilon equal to 1, let us make 0.1. So then you can see a deformation in the size and position of the limit cycle. Further, if you change the value of epsilon equal to 0.01, it further changes. And now you can see that part of the final trajectory, that means the attractor, is part of the solution of the algebraic differential equation. Then this part corresponds to the fast subsystem, that means more or less horizontal straight line. Again, this is a part of the slow subsystem, that is the line u equal to 0. And again, you have a part of the fast subsystem. And finally, if you choose epsilon much smaller, that is 0.0001, so then you can find this kind of structure. And I can assure you that visually it will remain unaltered for further decrease in epsilon. But if you have a closer look into the system, there will be mild deformation. But as epsilon tends to 0, this is more or less approximation of the final limiting trajectory as epsilon tends to 0. And these can be considered as a 4 different portion, 2 taken from the fast subsystem and 2 taken from the slow subsystem, and that actually constitute the final attractor of the given system. But what is the most important observation here? The important observation is the dynamics of the system changes from this to this due to the introduction of slow fast time scale. And now if we look at the 4 different concatenated portion of the solution trajectories, you can see this is a part of the fast subsystem. Then next one is the part of the slow subsystem. That's why it is marked with a single arrow. Then you will have another part of the fast subsystem, and finally it consists with the vertical part of the slow subsystem. So these 4 different parts, they actually constitute the final structure of the attractor. And there is different mathematical theory through which you can determine that where and how these attractors will be formed. And these are the mathematical theory, that is center manifold reduction, geometrical singular perturbation technique, blow-up transformation, singular Hop bifurcation analysis, determination of Carnot cycle, and relaxation oscillation. These are related with different mathematical analysis of this kind of system under consideration. So of course, natural question may arise that for a given system, can I perform all this type of analysis? Answer is that critical manifold you can derive for all the problem of this type. Geometrical singular perturbation technique was not that much modern technique. And in this case, what will happen that you cannot find out approximate expression for the manifolds, because mainly critical manifolds, because this singular perturbation technique cannot overcome the singularity at the cast point. And that's why blow-up transformation is required to understand or predict where the trajectory or attractor will be located. And singular Hop bifurcation is an interesting result, that once the model admits destabilization through Hop bifurcation, then as epsilon tends to 0, what we can see, a bifurcation becomes singular. So that means due to small change in the parameter value, we can see a sudden and large increase of the amplitude of the limit cycle, and that's why it is called singular Hop bifurcation. And Carnot cycle and relaxation oscillation, these are two classification of the resulting attractors, and mainly their classification as Carnot cycle or relaxation oscillation depends upon how the final periodic attractor is located with respect to critical manifold of the system. And if you are interested to have a detailed discussion of all the topics for the Rosenick-McArthur model, you can see this paper which was published in last year 2021 in Nonlinear Dynamics, where we have explained each and every part of this particular model. So now we consider a different model with slow fast time scale, that is called a simple preparator model with cooperative hunting. So cooperative hunting means that once predator is low in number, or they find difficulty in finding the individuals, sometimes it is possible, and we know several examples, that where the prey individuals are large in size, so therefore a group of predator attacks the prey, and they need some sort of group behavior. That means cooperation required from other individuals to have some successful catch. In order to model such kind of situation, this model was introduced by Alves and Hilker in 2017. Original paper was published in Journal of Theoretical Biology, and they have explained that the rate of predation, that means the success in the predation rate, will be higher with the increase in the magnitude of V. Of course, this model had a simple drawback. That means it can predict, or it assumes that the rate of success is infinitely large if size of the predator population is large enough. But that is not the ecological reality, because for any type of animal, we know there is a maximum group size for hunting is admissible. So that's why towards the end, I'll explain how this can be modified. Anyway, for this problem, if we introduce again the slow fast time scale, then what we can see through simple analysis, we can find out this kind of bifurcation structure. This blue color curve is the saddle node bifurcation point. This magenta color curve is the Hop bifurcation curve, and this red color curve is the global bifurcation curve emerging from the Bogdanov-Takens bifurcation point. And this vertical dotted straight line is the transcritical bifurcation threshold, and this transcritical bifurcation curve and saddle node bifurcation curve, they intersect at cast bifurcation point. And if you have a look at the details of the model, then you can find two different scenario. Either that means either you can consider the dynamics with respect to the parameter alpha and eta. Alternatively, you can have a look at the dynamics by looking at the parameter alpha and sigma as the bifurcation parameter, and accordingly you will have two different structure of the bifurcation diagram. But anyway, dynamics will be more or less same, but here we can see some sort of interesting behavior, because through one global bifurcation limit cycle disappears and through another global bifurcation limit cycle appears again and remain in the system for all higher values of this particular alpha. And this kind of discrepancy appears only for the unrealistic assumption that predator consumption can be infinitely large depending upon their total population size, and where they have assumed that the entire population will go for catching prey. That is not that much realistic idea. So anyway, what we can see, that interesting idea is that in this case we can see the large amplitude limit cycle without slow fast time scale. So whatever figure or whatever pictures I have shown you earlier, that gives us some kind of vague idea that in order to have limit cycle which consists of some part of the that is slow subsystem and fast subsystem, and trajectories are very close to the horizontal and vertical axis only when epsilon is very small. Rather, here you can see a completely different picture, that slow fast time scale can stabilize the system. This is the position and shape of the attractor for epsilon equal to 1. This is also the large amplitude limit cycle for epsilon equal to 0.5. And then limit cycle size is comparatively smaller when epsilon equal to 0.1. And in this case, for epsilon equal to 0.05, you see the coexistence equilibrium point is stable. So this actually explains two different scenarios. Depending upon the background reaction kinetics, the slow fast time scale either increase the size of the limit cycle or it can decrease the size of the limit cycle. That is completely determined by the background interaction involved with the system. So it never imply that introduction of slow fast time scale always leads to the situation that small amplitude limit cycle becomes a large amplitude limit cycle. Now we come to little bit discussion about the spatiotemporal pattern formation. So as I have mentioned earlier, the basic nature of the pattern can be classified into two different things, characteristics. One is the stationary pattern and another one is the dynamic patterns, where the different kind of patterns involves that spot pattern and labyrinthine pattern. These corresponds to stationary patterns. And dynamic patterns, they include traveling wave, periodic traveling wave, and other kind of dynamic patterns, as I have mentioned earlier. And here it is a partially complete list of patterns what we can see in case of interacting population. So this is a complete diagram for the pattern of a particular model, where we can see that this line is a Turing bifurcation curve, and this vertical line is the Hop bifurcation curve. And in this region, you can see some sort of stationary pattern, but beyond which you can find some sort of dynamic pattern. So of course, if in order to understand that why they are dynamic and why they are stationary, you have to look at the spatial average at the time evolution of the spatial average of both the components in order to understand these things. But what quick take home message is that once we are within the pure Turing domain, because if we are on the above this magenta color curve and on the left hand side of this vertical dashed curve, this magenta color curve is the Turing instability curve, and vertical dashed curve is the temporal Hop bifurcation curve. So in this region, the homogeneous steady state is unstable due to heterogeneous spatial perturbation, but stable under homogeneous temporal perturbation. So that's why it is called pure Turing domain. On the other hand, here what we have, that the homogeneous steady state is unstable due to both spatial perturbation as well as temporal perturbation. Although, on the other hand, in this domain, that means below the magenta color curve and on the left of this vertical dashed curve, this is the complete stability domain. Here homogeneous steady state is stable, But if you are means minutely look at the picture, then you can see that shading or color is slowly changing. So then you can ask me the question, then how you can ensure that these patterns are stationary or they are not changing with respect to time. This change in color is only due to the variation of the parameter, because on the horizontal axis I have taken a temporal parameter, on the vertical axis I have considered the rate of diffusivity, and as the homogeneous steady state changes with the temporal parameter, so that's why there is a slight change in the color. But through numerical simulation you can verify that these are stationary in nature. Again, in this domain, this is actually called Turing-Hopf domain, where you can find either stationary pattern or dynamic pattern depending upon the choice of the parameter value as well as your choice of the initial condition. And in this region, which is below the Turing bifurcation curve, but on the right hand side of the Hop bifurcation threshold, here also you can see some sort of dynamic pattern. But what is most important, mostly we can see spatiotemporal chaos within this particular domain. That means either in the Turing-Hopf domain or within the pure Hopf domain, but below the Turing bifurcation curve. This is our observation, and there is no mathematical proof behind this, and that's why it is quite challenging to find out the appropriate parameter value where we can find this spatiotemporal chaos. This is a recent publication in Bulletin of Mathematical Biology, that is in the context of effect of slow fast time scale on the resulting pattern, and where we have considered this type of spatiotemporal model, which is the modification of classical Rosenwick-McArthur model by introducing an alley effect. So this alley effect means the predator growth rate is not maximum at zero prey density. Rather, when prey density is very small, it is an increasing function of prey density. And these are the diffusion term. I'm sorry for this typo. This should be V. This is not U. And this is the ratio of diffusivity. And here we have the scaling parameter for time, that is epsilon, which lies between 0 and 1. But in this picture, what you can see, this is an interacting spiral chaos pattern which is obtained for epsilon equal to 1. And this pattern with same parameter value, just by changing the scaling parameter epsilon from 1 to 0.1, and this last one corresponds to 0.01, where you can see just a enlarged version of this particular part. So what is the important message from here? Important message is that with the increase in with the decrease in magnitude of the epsilon, the size of the arms of the interacting spirals, they are getting enlarged. And in this case also, you can see this kind of pattern if we increase the domain size at least 10 to 20 times compared to this one. So what we have done here, we just fix the domain size 900 cross 900 and perform the simulation with the same model just by changing the magnitude of epsilon. So what we can see, that this kind of spiral pattern remains spiral in nature, but the size of the arm or the patch size of the populations, those are significantly changing with respect to time. Also, if we look at the spatial average and their evolution with respect to time, so what we can verify that this pattern is chaotic in nature, this one is quasi-periodic in nature, and this becomes more or less periodic. And particularly for this parameter value, what we have observed, the dynamics of the spatiotemporal model is closely equivalent to the temporal model, that means without any spatial component. So this is not a surprising result, because for every model there is a parameter regime within the pure Hopf domain where the dynamics of the spatiotemporal model more or less equivalent to the dynamics of the corresponding temporal model. So that's why we need to understand that what kind of species which actually determines the values of the parameters is required in order to understand the dynamics will be different compared to the temporal model, and hence inclusion of space into the model system is important. Now we come to the last part of my talk, that is model with non-local interaction. So first of all, I'll explain what is the concept of non-local interaction. So in this case, I'm going to consider the space is assumed to be one dimension. And of course, one can ask the question how we can think about interaction over one dimensional domain. So for that purpose, what we can consider, we just consider we have a rectangular domain, and in the middle we have a horizontal line which is considered as x-axis. Now we have individuals located at different location over the two-dimensional domain. So at x1, y1 we have some individuals, at x2, y2 we have some other individuals, and so on. We can see at different points of the space we have individuals located at different positions. And now what we can do, we can actually map this density of the population on this particular horizontal axis. And if we do that, then for example, these are more or less on the same line, and we can project them onto this particular point, and therefore population density at this particular point, that is n at xj, is equal to sum of those n r x r y r, where r ranging from 4 to 7, because in the previous figure you can see that just for simplicity I have assumed this location as x4 y4, x5 y5, and up to x7 y7. So in this way, what we can do, we can actually map the population density at different location onto the horizontal line in order to have some sort of mathematical simplification of the distribution of the population over two dimension to one dimension, just to simplify the mathematical analysis. Now the important question is that why this non-local interaction is important. Idea is that once we consider the model with reaction diffusion equation, then interaction between u and v assume that individuals who are located at the same position, they are interacting among themselves. But we have assumed that both prey and predator, they can move from one location to other location. So the idea is that if they don't found enough number of individuals at that location, that means v who are located at the point x minus delta x, they are unable to find some individuals at the location x minus delta x, they can move to the position x also. And this is true for other special locations, that is x plus delta x, x minus 2 delta x, x plus 2 delta x, and so on. So therefore, the prey individuals available at this location can be accessed by individuals which are located in the nearby location. And as a result, what will happen, that this type of interaction term, that is u into v, that will be replaced by u tx times integral minus infinity to plus infinity phi of x minus y v ty dy. Here, of course, it is a continuous approximation or limiting case of this particular picture, because initially what we can consider that this u is competed or predated by the predators with this population density at different location. But of course, that will be multiplied by some function. In terms of mathematics, it is a kernel function, but actually this defines the probability that with which individual located at the location y come to the location x for have some successful catch. And as a result, what we can find, that based upon this assumption that individual located at x can be accessed by the individuals who are located in nearby location, that leads to modification of the interaction term u times v by u into integral minus infinity to plus infinity phi x minus y vty. And similarly, in this case, what we assume that cooperative hunting that is taking place over the non-local range, and as a result 1 plus alpha v times uv that will be modified by this particular integral. And here this phi satisfies two conditions. Number one, phi minus z equal to phi z. That means it is an even function. Ecologically, it means the movement of the non-local interaction is unbiased. So that means it can go either towards the left or towards the right with same probability. Second one is the mathematical assumption that this bounded variation is with constant support, but actually this assumption leads to the simple situation that homogeneous steady state of the original model, that means local model, remains an homogeneous steady state for the non-local model. So it will help us to compare the result, that means how they are changing due to the introduction of the non-local interaction. And for that reason, we consider phi z in this particular format. And if we combine these things into the model, then we can have this type of non-local partial differential equation where W1 Tx and W2 Tx, they are defined in this particular way. So here what we are we have assumed that non-local consumption of the prey by the predator, that is described by this one, and also non-local contribution to the growth of the predator species due to non-local consumption, that is modeled by W2 Tx, and that's why this u is now replaced by integral of phi 2x minus y minus infinity to plus infinity. And of course, the two kernel functions are different because contribution towards the growth of the species should be different as contribution towards the interaction which leads to successful consumption of the prey or catch of the prey by the predators. So these are the Turing instability condition for model without non-local interaction. And here you can see that involvement of the parameter epsilon plays a crucial role in order to determine the Turing bifurcation threshold, because Turing bifurcation threshold is given by solving this equation, that is replacing this inequality by an equality here. And of course, we can find Turing bifurcation threshold for different eigenmodes n, where n is a natural number, and the unstable wave numbers that can be given by these two expressions. And here we assume for simplicity phi z as a top hat kernel, which is defined by this one. So it is assumed that they can move at most a distance m either towards left or towards right. And for that, what will happen, that characteristic equation will be changed to this particular format, and where t and this d are given by these two expressions, and therefore Turing instability condition is given by this one. That means we have to solve these three equations simultaneously. And in this case, what you can see that from a homogeneous steady state, if we give a small perturbation for this particular parameter values without non-local interaction, because here we have the classical reaction diffusion equation model, we find stationary pattern. Here yellow color corresponds to high concentration, blue color corresponds to low concentration, and therefore you can see after certain time you can find some stationary distribution of the population. Now if we introduce this slow fast time scale, what happens that these stationary patterns are achieved over a means shorter time phase. So that means it actually reduces the transient time. So here you can see we need this much of longer time in order to have the stationary patches, but in the next case you can see the transients disappear quite rapidly, and we have the stationary patches much earlier compared to the previous case. Of course, I did not mention here the scale on the vertical axis, but time scale for both the pictures are actually same. This is from 0 to 1500. And now you can see that how it is changing with respect to different introduction of slow fast time scale and non-local interaction, just to see that this is a cross section of the pattern that we have observed in the previous slide. So this is a projection of uxt over tx plane, and now if we look at a particular snapshot of this particular surface at a fixed time, say t equal to 1500, then this surface uxt, its cross sections looks like this one. And now if we superimpose the patterns for different parameter values with non-local interaction as well as slow fast time scale, then we can see that how the shape and size of the patches are changing with respect to time. So earlier one was for just classical reaction diffusion model, and now if we introduce the case epsilon equal to 0.7, so you can see there is a significant change in the pattern. So size of the patches and height of the patches, they are also changed compared to the earlier one, which is shown as a dashed blue curve here. Now if we introduce the non-local interaction without slow fast time scale, then we can see that again the size and position of the patches, they are changed compared to the earlier distribution. And finally, if we introduce again the epsilon here, you can see another distribution of this particular species which has a stationary pattern. So this is a combination of 4 different patterns, and it actually explains that whether the size of the patch size is increased or population content is increased, or there is a possibility of localized extinction or not, and what is the maximum and minimum concentration of the population. All these things can be studied from this kind of picture. And these results can be understood clearly from this table. So here you can see on the left the values of sigma, eta and alpha remains fixed, and if we change epsilon and m step by step and determine the Turing bifurcation threshold, then you can understand that both epsilon and m have crucial effect on the determination of to determine the Turing bifurcation threshold. So for the reaction diffusion model without slow fast time scale, without non-local interaction, Turing bifurcation threshold is 0.178. Now if you introduce slow fast time scale, just 0.7 instead of 1, then you can see it changed to 0.125. Now if we return back to the original model, that means without slow fast time scale and introduced non-local interaction, then it changes from 0.178 to 0.244. And finally, again, if we introduce the slow fast time scale, again it changes to 0.171. And similarly, you can also determine the maximum and minimum of the unstable wave number, and this U bar, it actually calculates the average population content, whether they are increasing or decreasing with the introduction of slow fast time scale as well as for the introduction of non-local interaction. So here the values are calculated for a couple of different values of D. So these two corresponds to non-Turing cases, and these two corresponds to Turing cases, because for this model with cooperative hunting, interestingly, stationary pattern appears for D less than 1, in contrary to the classical cases of Preparator model where we can see pattern for D greater than 1. But it clearly shows that the value of D, range of non-local interaction, as well as the values of epsilon, they have significant effect on the total population content of the system. And these are some of our earlier work where we have done this kind of complete bifurcation analysis of the patterns in this particular paper. But now what we are planning, that how this kind of global bifurcation scenario for spatial pattern formation can changes due to the influence of slow fast time scale. Another thing is that, as I have mentioned, that we are going to modify this model based upon this recent publication, that is consideration of slow fast time scale not only into the system, rather some sort of alley effect in the predator growth. In literature, mostly people have considered alley effect in the prey growth, But in this article, we have argued that if we consider the two tropic levels and single tropic level with alley effect is admissible, so then if we introduce its resource instead of its consumer, then we can have a preparator model with alley effect in predator growth. So our future goal is to study that this kind of model in the presence of slow fast time scale, as well as with respect to the spatiotemporal pattern formation without and with non-local interaction. Finally, I must mention that I told you earlier that how the unlimited consumption cooperation rate can be modified. So that cooperative hunting term can be modified as 1 plus alpha v by beta plus v. And here you can see that if v equal to 0, so there is nothing to cooperate. And with the increasing magnitude of v, that means with the increase in the population density, there will be an increase in the cooperation level, but it should not be unbounded above. Rather, it will be bounded by the value alpha, and here beta plays the role of half of the strength of the maximum possible cooperation. So this is our another future goal to work with, that is preparator model with hunting cooperation, but with a saturation, that is not with unlimited growth. So now references, these are some classical references on slow fast time scale. If you are interested, you can have a look at this book. It gives a very nice introduction to the model with multiple time scale. And these are some other relevant papers and articles where they have talked about transient dynamics and effect of slow fast time scale. These are some of our work in the area of pattern formation and the model with slow fast time scale, as well as non-local interaction. And before coming to the conclusion, concluding my talk, I must thank the person, Professor Vitaly Volpart, who actually dragged me in the area of non-local interaction. And my other collaborators are Papan Saha, Pallab Jyoti Pal, Kullan Manna, my current PhD student Pranali, and Sergei Petrovsky. So whatever I have presented today, I have worked out this problem with all of them. And thank you very much for your kind attention.
Thank you very much, Professor Banerjee, for a very fascinating presentation, particularly of your recent works. I think we have really enjoyed your talk. And now the floor is open for questions. So the audience, they can ask any questions, comments, suggestions. So you're welcome to ask. Yeah, Prasant Singh. Yeah.
Hello, sir.
Hello.
Yeah.
Sir, in the I have a confusion that preliminary part, sir. Sir, in math modeling of pattern formation, to define a change in the geometry of patterns, so how noise term can be added into PDEs, modeling PDEs? So
okay, actually there are 2-3 different approaches. Either you can introduce some additive noise or some multiplicative noise, or you can introduce demographic stochasticity by considering the population as a stochastic variable. But the simplest possible way out is that if you have some parameter into the model and you have an appropriate justification that this model can be varied due to some sort of stochasticity, either due to environmental stochasticity or due to demographic stochasticity. And also, if you know the range of variation, then you can introduce some function like alpha 0 plus alpha 1 xi t, where xi t is the desired noise term. But in this case, the type of noise is required to be chosen carefully, and the noise strength is required to be chosen carefully in order to ensure the positivity of the solution. There are plenty of literatures which are published in various popular journal like Science, Scientific Reports, and etc., where people have considered just additive noise. But those kind of model cannot be proved that solutions are always positive. So you have to be careful about the introduction of the noise. So if your parameter appears as a additive parameter and you perturb the parameter alpha by say alpha 0 plus epsilon xi t, then it will be a additive noise. Or if this parameter is multiplied with some of the variables, that is either v or v square or uv or some other thing, accordingly you will have the multiplicative parameters into the system. And if you are interested, you can have a look at the book by Alberto Donofrio, that is Model with Bounded Noise. That is a newly emerging area where he have explained that instead of considering either white noise or colored noise or pink noise, we can consider some sort of bounded noise in order to ensure, although it is a noise term, but it never go beyond the desired level, because most of the noise terms are actually driven from normal distribution, and theoretically normal distribution can take any value from minus infinity to plus infinity. One can argue that if with any help of random number generators, if we generate the random numbers, then it cannot generate any number beyond the interval minus 20 to plus 20. That is fine. But again, you have to understand that is the limitation of the noise generator. So it would be better to consider bounded noise in order to introduce noise into the system.
So have you considered the effect of noise in your models?
In only one paper that I worked with Anirban Chakraborty from JNU, but otherwise, because the thing is that there is no such detailed mathematical tools with which we can study, because ultimately you need to look at the average distribution and need to take several simulation run of the same stochastic PD and look at the average distribution, whether it is different from the model without noise or in the presence of noise, it gives rise to some other type of dynamics. And I must mention here that model with additive noise of course reveals some new dynamics, but as I am working in the area of population dynamics, so from mathematical point of view as well as biological point of view, the model with additive noise cannot be proved that solution will remain always positive. So that's why I did not consider these things in details.
Okay. So any other questions?
Sir, actually, sir, here itself, I was thinking that because I do not have much knowledge in that, so I was thinking that it could be meaning in PD we have some force term in the right hand side, like sine omega t, for example, and that omega can be random frequency. So in that way, can we think of like a random noise to the particular PD?
Yes. Actually, if you look at some of the works by Professor Devshankar Rai, who actually delivered a talk couple of weeks back in this particular series, he had couple of papers in Physical Review E and also Europhysics letter, where he actually given some sort of dichotomous noise or some non-uniformly distributed noise in this kind of PD. And one of his student, Pushpita Ghosh, she also works on this kind of problem, that is spatiotemporal model driven by noise. So you can have a look at his papers.
Okay. So any other comments or suggestions?
Sir, I have one doubt. Do you have any model where this slow time scale is multiplied with the predator population, prey population?
There are a couple of articles by Sergio Rinaldi in 1997 and earlier.
Okay. Which one is more realistic, sir? Why do you particularly multiply it with the predator population?
Actually, in general, if you look at any kind of trophic level, mostly predator population grows over a slower time scale compared to the prey. If you consider the interaction between vegetation and cow or goat or giraffe or zebra, you can see that growth of giraffe, zebra, etc., that means the herbivores, those are taking place over a slower time scale compared to the vegetation. Similarly, if you consider the consumption between these herbivores with their carnivore predators like tiger, lion, necre, hyena, etc., they are actually growing over a slower time scale compared to their prey. Even in the case of phytoplankton, zooplankton, the growth rate of zooplankton is much more slower compared to the growth rate of the phytoplankton. So that's why mostly we consider the slow fast time scale in the, that means slower time scale for the predator and faster time scale for the prey. So in other words, in the context of prey predator model, the consumer or inhibitor is slowly growing compared to the producer or that means activator.
Okay, sir. Thank you, sir.
Yeah. Any other questions, comments? Yeah. So I have a couple of questions, Professor Banerjee.
Yeah, sure.
So the introduction of slow fast time scales in your models, so they are based on the physiological experimental results, biological experimental results?
Yes, some sort of ecological evidence about their growth rates.
Okay, so based on that only you introduce the parameter epsilon in the appropriate terms.
Yes, yes.
So what about neuronal systems like Fitzhugh-Nagumo equations? So
those are actually origin of this kind of slow fast system. Those are actually origin of slow fast time scale, and recently we are trying to introduce this kind of things in case of cancer biology. That means different pathogens, or that means the effect of chemotherapy, etc. They are actually taking place over different time scale. So that means the local time scale, global time scale, and how to introduce slow fast time scale into that thing. And also, as you have mentioned, neuronal model, mainly from the brain signaling dynamics, there are several multiple time scale. And if we consider, say, 3 species model, then the question is that how to introduce slow fast time scale parameter? Only one parameter into 2 equation, or 2 different rate constant in 3 different tropic levels. So that means for x, y, z, either y and z both growth equation will be introduced with epsilon, or y will be introduced by epsilon 1 and z will be introduced with epsilon 2, such that the magnitude of epsilon 1 clearly different from epsilon 2. And there are couple of literatures in this kind of problem, but they are mostly dealt with the problem where equilibrium point can be obtained explicitly. But rather, I am interested to study, as I have explained in 2 or 3 slides, that where the slow fast time scale have a stabilizing effect on the system dynamics. Mostly available literature, they talked about that introduction of slow fast time scale drives the system towards instability. But there are some other examples also. It can have also stabilizing effect. But you are right that the main origin of this slow fast time scale is the neuronal dynamics, that is Fitzhugh-Nagumo and other kind of neuronal models.
Okay. Yeah. In one of your tables that you have shown for the non-local interactions, I found that introduction of slow fast time scale plus non-local interaction seems to give results almost close to the classical case.
That is actually for because I have explained only one parameter set for this this demonstration purpose. But as I have shown you the pattern diagram, if we consider that kind of pattern diagram with varying epsilon, that means strength of the slow fast time scale and also the strength of the non-local interaction, then we need then we can see completely different kind of dynamics. That means at that particular level, the role of non-linearity will comes into the picture. And also we can check that if we introduce non-local interaction term only in 1 interaction term, or in 2 interaction term, or maybe in other terms also. But Mostly, once we try to publish this kind of results, people are asking for, okay, you are talking about if solution exists, can you prove that there exists a solution for this kind of problem? So in order to make our life simple, what we have considered that non-local interaction kernel, they are same for both the equations. Their range of non-local interactions are same, but in reality, they are different. Okay. And just to explore, of course, I should be sorry that I was not able to explain that point clearly. That's why I have shown a global bifurcation diagram where the non-local interaction can lead to several kind of global bifurcation. That means changing traveling wave to periodic traveling wave, even to modulated traveling wave, and even for certain parameter regime, it can transform to stationary patterns also. So those kind of scenarios with respect to slow fast time scale is required to be explored. That remains unexplored as far as my knowledge goes.
Okay. Yeah, one last question. Do you come across solitary wave type solutions in your models?
No. I mainly studied the pulse and moving pulse and other kind of things, but never tried with solitary waves.
Okay. Yeah. So are there any other questions? Yeah. If not, let us thank Professor Malay Banerjee for a very beautiful and fascinating lecture. And I'm sure all the students and scholars have enjoyed your talk. So I do hope that you will be able to visit our department.
Sure, definitely.
And I wish you all the best in your endeavor. Thank you very much. Thank you. Yeah, we can now leave. Okay. Yeah. Thank you very much. And Professor Sendilvalan will contact you for further details.
Sure.
Okay. Thank you.